So we're going to have a look at this first example, which I've got our compound angle formulas here. So let's try and get them in. Which says to us, solve for theta if cos theta times cos 24 plus sine theta times sine 24 is equal to 0.715, and theta is an element of negative 90. Silly of me. Negative 90 to 90. So let's just put in the negative there. Right, do apologize, negative 90 to 90. Alrighty, so guys, remember when you are doing your general solution, and this is just a particular reminder for when you start going through past papers, there are a couple different ways that you can go and solve them. So your answers might look a bit different. If you're really unsure, basically all you do is that k times 360 or k times whatever it ends up being. If you just keep adding whatever that product, that coefficient of k is to your answers, you should eventually get the same answer as the memo. So there are different ways to solve an equation. The way that we do it with the reference angle is the way that most people do it, which is generally the way the memo will be set up. So you shouldn't have a problem, but just bear in mind that sometimes answers do look a bit different depending on how someone's chosen to solve an equation. Okay. So looking at the equation that we've been given, hopefully what we're noticing is this is a compound angle formula. We've got a cos plus a sine. And when we've got cos plus a sine, we're working with the compound angle formula of cos A minus B. Right, so what that means is we can apply our formula here. Get a better pen going. So the cos A minus B formula essentially says that we can reduce this to cos of theta minus 24 degrees. If you look at the formula that I've highlighted there in our compound angle formula, that's what it reduces to. So once we've essentially simplified and reduced that compound angle expression to just one single term, we know it's still equal to 0.715 because all you've done is taken this left-hand side and simplified it. You haven't changed its meaning, you've just simplified it. And this is now where we need to start solving our general equation. Right, I'll try to write down steps as we go along, just so that you have some steps that you can potentially follow. For some people, it is useful. So the very first thing that we always want to do, can't write one there, okay, is isolate your ratio. What that means is that there should be no coefficient to the ratio. So if there was a 2 there, I would need to divide the 2 away. I shouldn't be adding or subtracting anything, so it shouldn't be cos theta minus 24 plus 3. I shouldn't have that. The only thing for me to have when I isolate my ratio is cos, tan, or sine, and the angle. The angle can have lots of things going on, but it must just be the cos and the angle. So this one's already isolated for me. I'm sorted there. The next thing I do is I find my reference angle. Right, your reference angle is where you use shift on your calculator. And to work out your reference angle, remember you ignore the sign of your ratio. The sign will become important when we decide which quadrants it's in. Now, in this case, this is a positive, so the sign thing doesn't really matter. So what I'm now going to do is I'm going to type shift sign on my calculator. I'm not, because it's cos. I'm going to type shift cos on my calculator. And remember what it does is it gives me that cos to the -1. And in the bracket, I'm going to type 0.715. And that's going to give me my reference angle. Okay, so type shift cos 0.715 for me in your calculators. And in the chat, tell me what reference angle you get. And great tools, just remember, if you have any questions at any point or anything, just pop me a message in the chat. Unmute yourself, raise your hand, whatever you need to do or you're most comfortable with, but please do let me know. Okay, so shift cos on your calculator. So shift cos of 0.715. In the chat, what is your reference angle? Nice, guys. Well done. Okay, so most of you are giving me to 2 decimal places. That's absolutely fine. All right. If you feel more comfortable, or if you feel comfortable working with 4 or 5, it is slightly more accurate, but honestly, it's not something that we're going to penalize you on. All right. So 2 of you have given me an answer. The reference angle, I don't know why I wrote 3. 44,3, I'm going to just do 3 decimal places. But honestly, if you said 0.36, it's absolutely fine. There's nothing wrong with that. Excuse me. All right, so now we've got our reference angle. Once we have got our reference angle, we now use the sign of the ratio to determine the quadrants. Now, when I said to determine the quadrants, remember any trig quadrants. Any trig equation has 2 potential solutions. So there's 2 places in all 4 quadrants where sine is positive, where cos is positive, and where tan is positive. So that's what I mean by determine your quadrant. So we would want to determine where cos is positive in this case. Now this goes back to your cast diagram, which I'm going to put in here. And you decide where it's positive. So in this case, what we have is a positive cos. And so what we're looking at is quadrants 1 and quadrants 4. Quadrants, or the quadrants that we're working in, determine for me which reduction I should now go and apply. So it would help if I could number as well. So based on my quadrants, I apply the appropriate reductions. Right, now you've seen this because we've done equations in our very second lesson that we did together. When I do my two solutions, because there should always be 2 solutions, I just like to number them according to my quadrant, or label them according to my quadrant. So I've got quadrant 1 and I've got quadrant 4. That's where cos is positive. Should be enough space for me. We'll see how we go. Once we've done the shift cos, the cos falls away. I no longer need cos because I've got the angle that is appropriate for the specific ratio I'm working with. What I now do is I equate the angle to the reference angle and apply my reduction formulae. So just a reminder, the angle that we're working with here is the theta, apparently not going to highlight, is the theta minus 24. So that's what we now equate to our reference angle with reduction formula where necessary. So theta minus 24 is equal to, now quadrant 1 is just theta. So it's just going to be equal to the 44,356 or 36 for those of you that rounded off, plus k times 360. Now you always have to have this k times 360 whenever you start dealing with your angles. As soon as you said shift cos, you should have plus k times 360. K is an element of the integer number system. The second. Now we start to solve. Remember, we're solving for theta. So that means through inverse operations, I'm going to add 24 on both sides of my equation. And so what that means is I get theta is equal to 68,36 degrees plus k times 360, where k is an element of the integer number system. That's your first solution. Now, I'm not going to underline it just because in the question, so in the actual question that I was given, remember we were given a very specific range for my angles of theta, which I'll get to in a second. Right, so that's my first solution. My second solution is now in quadrant 4. Same thing, I take my angle, theta minus 24, and I make it equal to, and in this case, because there's a reduction that I need to apply, I must do so. Quadrant 4 is 360 minus theta, so 360 minus my reference angle of 44,356. And then again, because I've now started working with angles, I need to have my plus k times 360, blah, blah, blah. All right. Now we go and solve. Obviously, if you can do the 360 minus and the inverse operations all at the same time, by all means, go for it. So it would be 360 minus the 44,356, then plus 24 degrees, which gives you 339,644 4 degrees plus k times 360. Right, these two things that we have just found are what we call the general solution. I'm just wrong thing that I'm. So these two final answers that we've just found are your general solutions. So sometimes in the question, it will say determine the general solution of, you stop there. But because we were given this interval of theta is an element of negative 90 to 90, we now need to list the specific theta values that fall within that range. We now use our general solution to go and do that. Right, so from quadrant 1, and I'll write my answer neatly in a second, I need all of the theta values that fall between negative 90 and 90 included. So the value for theta that I got was 68,36. That definitely falls in that range. So that's definitely one of my solutions. To now get the rest of them, I use that plus k times 360. So I'm going to keep adding 360 or subtracting 360, however many times, to get all solutions within the domain that I've been given. Now, obviously, if you say 68,36 plus 360, you're falling way outside the maximum of 90 degrees. So we don't have to add. If we subtracted 360, you would end up at like 298, 291, something. That's way, way outside the range up to negative 90. So actually the only solution I'm concerned with here is 68,36. That's from solution number 1 in quadrant 1. Then I go to quadrant 4 and I deal with the solution there. So my answer there was 339 degrees, 64. That's way outside the range. So I don't want that. So now again, I start adding and subtracting 360. I'm definitely not going to add 360 because that's going to take me up to what, like 699? Way, way, way outside my domain. Not even going to bother. But if I subtract 360, when I subtract 360 degrees, so if I say 339,64 minus 360, so that's where now k would be equal to negative 1, so k times 360, I get negative 20,36. Now, negative 20,36 falls within that domain. And so what that means is that this is a potential solution that I can have. And so what I've now established is that based on the defined domain of negative 90 to 90, my only values for theta that I'm concerned with are negative 20,36 degrees and 68,36 degrees. Those are the only values for theta that satisfy the equation I've been given in the specific domain of theta is an element of negative 90 to 90. All right, so when you are given a specific domain, you need to be very, very careful to actually go and find the specific solutions appropriate for that domain. All righty, so there's your first example. I don't think I really need to do any other steps here. Maybe I can just add one more. So equate angle to reference angle with reduction formula. And the final step would obviously just be to solve for your angle. Right, I know the steps might for some of you be an irrelevant thing, you just know how to do it, but for some people it is really useful to have a set of steps to follow in order to do something. So generally speaking, if you're going to apply these 6 steps, isolate your trig ratio, work out your reference angle, use the sign to find your quadrants, apply your reduction formulae where appropriate, equate the angle, and then solve, you're going to be able to solve any general solution I give you. Alrighty, so that's really it. Reference angle is really important, quadrants really important, so that you can find your reduction formulae, but that's really it when it comes to finding the general solution and then a step further, specific solutions if you are given a domain. Okay, so guys, screenshot this and then you're going to try one by yourselves. Now, guys, equations obviously become important in graphs. If you think about where we use equations in graphs, it's things like points of intersection. It's things like if you subtract two graphs to find a distance. So the idea of solving an equation, really important when it comes to functions. Okay. Right, so this is the one you're going to try by yourselves. Cos 4 theta times cos 40 plus sine 4 theta times sine 40 is equal to -1. I have not given you a restriction on your domain, so you're just finding the general solution here. There's no specific theta values you have to find. It's just a general solution. Give this one a try for me. Remember, if you've got questions, just ask. You can send me a direct message. You can put a message in the chat, whatever you prefer. You can unmute yourself if that's what you prefer. But let's give this a try, and please do ask if you've got questions. Alrighty, let's have a look. Okay, so guys, for this one, again, it was very similar. You had a compound angle situation going on. Again, it was the cos A minus B. So you could reduce that to cos 4 theta minus 4t equals -1. Now, -1 is actually one of those special angles that we've spoken about before. But even if you are not 100% sure of what's going on, you follow those 6 steps. All right, so we found our reference angle. Let's just find your reference angle. That's 180 degrees. Now, 180 degrees is a little tricky because of the fact that it falls on an axis. But then again, use that sign of your ratio to determine which quadrant you're working in. This ratio is negative, so it's where sine is negative. Sine is negative in quadrants 3. It also helps if we're working with cos here. Cos is negative in quadrants 2 and 3. So that's how I knew which quadrants I could work in when it comes to my specific general solutions. Now, be mindful of the fact that in quadrant 2, it's 180 minus. So 180 minus 180 is obviously 0. And so then it's just a case of adding the 40 to 0. So that's why it was just 40. The other thing I just want you to bear in mind is because of the fact that this is a 4 theta, to solve for theta, you have to divide everything by 4. That includes your 360. 360 divided by 4 is 90. So if you were now to go and work out specific solutions, because let's say I gave you the domain and said theta was between these values, you would now add a 90 every time to your solution, not 360. So you work with the general solution you've found. Right, same thing when it then comes to quadrant 3. The reduction is 180 plus, so it'd be 180 plus 180, which is 360. And then again, you apply your inverse operations. Once again, it's 4 theta, so you'd be dividing everything by 4. So just bear that in mind as you go along. I've said this to you before, once you've sort of gotten past the trig stuff, applying your identities, your formulas, it's then just algebra. So all of this, once you've done the compound angles or the double angles or whatever, it's just algebra. It's solving an equation using inverse operations. All right. I'll wait in case you want to take a screenshot, and then we're going to have a look at another example. I've just got a question of my calculator gave me. Listen, Mitchell, it's entirely possible that I was a bit of a non-child and use sine, because as we saw, sine was in my head. Let's just make sure. Shift cos -1. 180. I'm about to do something that's probably really stupid. So shift cos -1. Also, please just give me a second because I'm being a bit stupid. Yeah, I know what I did. I used my reference angle with a negative. Guys. Aye. Right, thank you. 0. So this would be 180 minus 0. Sorry, Mitchell. Sorry, everyone. This is what happens when I try and mix things. I never actually solve equations like this using a reference angle, and clearly my brain was a bit much when I did this. Right, I do apologize. I will quickly fix it. 180 plus, okay, divide everything by 4. 180 divided by 4 is 45. So it should be 45 plus k times 90. Thank you. 180 plus 0 is then just 180, which is 220. 4 is 55. Okay, do we agree with this now? Mitchell, just let me know, because like I said, I clearly got my own brain confused. Do we agree? I'm gonna take it as yes. If we don't agree, you can say so. I do apologize, grade 12s. Like I said, I usually do not use a reference angle, and I just got my brain confused. We fixed it, it's fine, mistakes happen, life goes on. We fixed it, you can take a screenshot of the correct one now, and then we're gonna look at example 2, where my brain is working and I won't make a stupid mistake again. All right. Oops. So example 2, now we've just been asked to find the general solution. There's nothing about restricted domains or anything like that. So we're literally just going to find a general solution. We stop at the plus k times whatever we end up with. So here we've been given sine 2 alpha plus 2 sine alpha is equal to 0. Now, guys, what I want you to take note of, like off the bat, is the fact that 2 alpha and alpha are not the same angle. One is a double angle. When you are solving trig equations and you've got multiple ratios that you're working with, the ideal is that they're the same ratio. So the fact that this is both sine is already a good start. But even better, the angle should be the same. If your angles are then the same, you can start adding like terms and so on. But here, my problem is that those angles are different. I've got a double angle and I've got a single angle of alpha. Now, what that means is I need to think about how can I take a double angle and create a situation where I no longer have a double angle. And that's through our formula. So remember, sine of a double angle is the one where there's just one, so it's not like you have to question anything. So this now expands to 2 sine alpha, cos alpha plus 2 sine alpha is equal to 0. All right, so where possible, you need to have all of your angles the same. If they are not the same, it's not the end of the world. There are other ways that we can go and deal with this, but it does make it a lot harder. So when you've got a double angle and a single angle, immediately anyways, you should be thinking, oh, that's a double angle. Reduce it to a single angle alpha or theta, whatever it is, and then work from there. Now that I have this situation, I can start solving. I still have 2 terms and now 1 term as a cosinus. But remember, anytime you're solving something where there is something common in both of your terms, and that's what I was saying earlier, 2a or 2 alpha and alpha are not the same thing. So technically, it's not common across terms. Now that I do have both alphas, what I now have is a highest common factor across both of those terms. And so what that means is I can now start to factorize. Now, even more, I've also got a 2 common. So I can take out 2 sine alpha, leaving me with cos alpha plus 1 is equal to 0. Remember, what you've essentially done here is you've dealt with this as like a quadratic equation, as a factorizable equation. And remember, anytime you're working with a quadratic equation, you should have one side equals to 0. And once you have factorized, you can now make each of your factors equal to 0. And so what that means is we can now say 2 sine alpha is equal to 0, as well as cos alpha plus 1 is equal to 0. When you are factorizing in order to solve, what does end up happening is you've got 2 equations that you're going to have to solve, which at the end of the day means you potentially have 4 different solutions. Sometimes it happens that the solutions end up being the same, and that's fine. Not always, but sometimes it does. All right, so once we've got these 2 equations, we follow those 6 steps. It doesn't matter which one you choose to work with first, okay? You're going to get all 4 solutions in the end anyways. So let's go with this 2 sine alpha. Remember, the first thing is to isolate your ratio. So I'm going to divide both sides by 2. So sine alpha is equal to 0. Again, this is a special angle, but anyways, we follow our steps. Now I'm darting everything I know. If you now say shift sine of 0, you get 0. So your reference angle is 0 degrees. And now you go and work with your quadrants. Now your ratio here is 0, okay? So it's a bit of a tricky one, but 0 generally we consider as a positive value. It doesn't technically have a sign. I'm fully aware of that fact. But when it comes to trig and things like nature of roots and stuff, we consider it as a positive value. So we have to ask ourselves, where is sign positive? Sign's positive in quadrants 1 and 2. So the quadrant 1 solution is where I take the angle alpha and I make it equal to just my theta, so just my reference angle, which is 0, plus k times 360. And that's actually done. I don't solve anymore. My second solution in quadrant 2 is where we've got alpha of 180 minus my reference angle. But 180 minus 0 is 180. And so for my first equation, I've got my two solutions. Okay, so that's the first one done. Now I have to go over to the cos. So step number 1 is isolate your ratio. So cos alpha is equal to -1. I'm not going to make the same mistake. We now say shift cos of 1. Remember, we ignore the sign. I need to listen to my own steps. And we get our reference angle is equal to, that's 0 degrees again. Again, we're thinking about where cos is positive. So cos is positive in quadrants 1 and 4. Okay. Quadrant 1, we actually already know what the situation is. It's alpha is equal to just your reference angle, so 0. And then your second solution in quadrant 4 is 360 minus, but 360 minus 0 is just 360. Oops. Okay. What I hope you notice is the fact that in your two solutions, well, out of your 4 solutions, I should say, 2 of them are actually the same. So this quadrant 1 solution for both the sine and cos ratios are the same. It kind of makes sense, okay? In quadrant 1, both sine and negative are positive. There's a co-ratio relationship with them. We end up with the same solution. If you only write that solution once, that's fine, all right? But what I always say is rather just write everything down. If there's a repeated solution, who cares, right? It's not like you're going to be penalized. Or we don't do negative marking. We're not going to penalize you for writing the same solution down twice. Rather have it there than start confusing the situation. But if you did notice it was the same solution, you only wrote it once, that is absolutely fine. There's nothing wrong with that. Okay, so this example showing you the fact that sometimes we need to use our double angle formulas to be able to expand to get single angles. And then we can potentially go and solve. Sometimes we have to use factorization in order to solve. And then if you are factorizing, what it often means is that you're going to have 2 equations that you solve. So you end up having 4 solutions. All right, but let's take a screenshot of this one. And then I'm going to give you one to try. Oh, okay, Mitchell, sorry. There was a question, where is cos negative? So remember, cos is negative in quadrants 2 and 3. This thing wants to work. Sometimes technology really. Okay, so cos is negative in quadrants 2 and 3. And so in this case, I'm really having a time of it tonight, aren't I? Jeez Louise. Yeah, Mitchell. Clearly, cos and I tonight are not on the same page. That's what's happening. Cos is negative in quadrants 2 and 3. Thank you. Boy, guys, it isn't even halfway through the term. So quadrant 2, 180 minus my reference angle, so it'd be 180 plus k times 360. And quadrant 3 is 180 plus, which is obviously 180 plus 0, which is just 180. Again, my statement still rings true. We have the same solution here. You don't have to write it twice. Okay. But yeah, cos and I clearly don't see eye to eye tonight, which is fine. I'm not going to hold it against cos. But thank you for checking me. Guys, who knows why cars? I usually like cars. It's hating on me tonight. Maybe the next cars I'm going to feel more comfortable with. Oi, oi, oi. Okay, well, you guys are on it, which is great. Clearly, it's been a day for me. Right, next one are back. Okay, you try this one. What I want you to just note is that it's sine squared. Okay, if it helps you, think of this at home, and the technology is fighting me. If it helps you, think of this as 2x squared plus x equals 3. So this is a situation where I'm saying x is the same thing as sine beta. Remember, I've said this to you before. If thinking of your terms in terms of a variable is helpful for you to be able to solve or to simplify whatever, do that. So this might help you, this 2x squared plus x plus 3 might help you in understanding how to now go and solve this equation. But give it a try. We've just used one way this factorization, so that's going to be important here just as your hint. And I'm going to contemplate a few things because I need to get cos right, clearly. Right, guys, let's have a look. So this one, a little trickier in terms of the factorization, because like I say, you had to see the trinomial. Okay, now I said earlier, if you feel more comfortable, envision this as 2x squared plus x. Okay, that's not going to work there. So 2x squared plus x equals 3. So standard form would mean that you've got 2x squared plus x minus 3 equals 0. If you now go and factorize that, you get 2x plus 3, x minus 1. And because we've said that those x's are the signs, that's essentially what you're dealing with in your factorize step. So once you factorize, remember I said you have to then take each of those factors, make them equal to 0, and you've got 2 solutions that you get. Now, just quickly, shift sign of 1.5 gives you no solution, right? The reason for that is because sine as a ratio is either opposite over hypotenuse, or if you think of it on your Cartesian plane, okay, whatever, it's y over r. What you need to remember is that your hypotenuse, or the radius on the Cartesian plane, is always the longest side, always, all right? So r will always be greater than y, or hypotenuse will always be greater than the opposite, always. If that's the case, according to those fractions, you can only ever have a common fraction. You can never have an improper fraction. And because this is then an improper fraction, or greater than 1, you will have no solution. So this is both true for cos and sine, because cos is adjacent over hypotenuse, or x over r. It's a similar thing. So for cos and sine, for a real solution, your ratio must fall between 1 and -1. If it is greater than 1 or less than -1, you're going to get a no solution. Obviously, you'll just do it on a calculator and you'll see no solution, but there is a reason for it. And if you can start to, if you can start to see and identify, oh, I automatically know that's not going to be a solution, you don't have to waste your time. You can just say no solution. Okay, I'm darting everything I know. So for the second one, sine beta equals 1. Reference angle, shift sign 1 is 90. Yes, which it is. And then you go and find your general solution. So this is where sine is positive. So quadrants 1 and 2. Quadrant 1 is just 90. Quadrant 2 is 180 minus, so 180 minus 90. And once again, hopefully what you realized is that you end up with the same solution. So in both cases, you've got 90 plus k times 360. You don't have to write it twice. If you do, it doesn't matter, but you don't have to. It's exactly the same solution. So if you did write it twice, no problem whatsoever. If you didn't write it twice, it's also absolutely fine. It is the same solution. When you say not finding the reference angle, do you mean like not finding it at all, or finding the reference angle but then just not writing as I do reference angle? Because the thing is, you have to find a reference angle to solve the equation, unless you are using a different method of solving the equations. So like I say, I usually don't actually find a reference angle. I use a different method to solve trig equations. So unless it's a completely different method, you actually do have to find a reference angle and then solve from there. So yes, you will be penalized if you don't find the reference angle. If you just mean you don't write down the step of reference angle equals, then no. If you work out the reference angle and you use it appropriately, you just don't specifically say reference angle, you won't be penalized. But you do have to have a reference angle if you're going to solve it like this. If you use a different method, like I say, then no, it's fine. There are ways to solve equations without a reference angle. And then no, you don't have to find one. Very much depends on what you've been taught and what your method is. All right, guys, so take a screenshot. Just a reminder, obviously today is Wednesday and there's a quiz. It will be on your classroom in a few minutes. And a second reminder of the fact that we are starting geometry on Monday. I won't be with you for that lesson just because I've got parent meetings that evening. So unfortunately, I have to be there. But you are in very capable hands. So there will still be a lesson. We will just have a substitute teacher for that lesson. We are starting with circle geometry. So you're going to be going through some circle questions. We're going to carry on with circles on Wednesday next week. So there'll be more time for circles. And then, as I've already explained to you, we're going to start with the grade 12 similarity and proportion. And like I say, won't be with you on Monday, unfortunately, but there is still a lesson. You will be there, and you will be starting with Euclidean or circle geometry. Alrighty.